what these are together first. If you just type in 4084.1 times 60 divided by 12 divided by 5280, this is going to be wrong. On your calculator, that'll be wrong. Because you've got to put these together in parentheses with multiplication. Questions there? Good? All right, this one's kind of a cool one. I like this problem we're going to do here. Where is it? Yeah. May I erase this, please? All right. So the Earth is roughly a sphere, right? Roughly, it's a sphere. So if we take the Earth, right? Here's the equator. San Antonio is not on the equator, right? We're in the northern hemisphere. So we're somewhere along here. I'm just going to put like this is San Antonio, somewhere around here. Now, the Earth, right, rotates on an axis that goes through the North Pole and the South Pole, roughly, all right? I mean, it's not perfect, but again, imagine an axis of rotation. The Earth is going around. How long does it take for San Antonio to go around that axis of rotation one time? Roughly 24 hours, right? That's a full day, right? You go around like that. We good? Now, if you look from the top down, from the North Pole, if you're looking straight down, then you'll see that we are traveling in a circle like this, aren't we? When we go around? Yes? So let's look at that from the top down. Here's the North Pole, and then we have that red circle like this. And then San Antonio is, somewhere around here. This is from the top view. This is the Earth. That's supposed to be the center. That does not look like the center. It doesn't even look like a friggin' circle. All right? Okay, so here's what I'm going to tell you. The distance from the center of the circle to San Antonio, what I'm talking about is the distance from here to here. That distance right there is about 3,430 miles. 3,430 miles. What do you think I'm going to ask you now? Not how far we travel, how fast we're traveling, right? What is our linear speed? What is the linear speed of San Antonio around the center of the Earth? Right, because you could look at us as right now being like a point on a bicycle wheel going around, right? So we're going around like this as the Earth rotates. It takes 24 hours to go around, right? So let's find the linear speed of us, okay, sitting right here in this room, about the axis of rotation, right? About the axis over here. So we want to know relative to that, how fast are we moving? So what's the formula? The one we've been using, right? Linear speed. Now the book calls linear speed v. All right, I believe they do call it v for velocity. Yes, they call it v. All right. So in the book, this is linear speed. All right, so v is s over t. But s is what? R times theta. We have that formula over t. Do we know our radius? Yes. Do we know the angle? So 3,430 miles, right? Times, do we know the angle? Well, we do a full rotation in 24 hours, right? So I'm going to write that down here. We do 1 revolution per 24 hours. We could say 1 revolution a day, couldn't we? But I'm going to say per hour. Because our final answer, we want it to be in miles per hour so that we can kind of understand what the speed is. So you agree 1 revolution per 24 hours? Which for us, we need it in radians. So this 1 revolution is really what? 2 pi, right? So here my angle is going to be 2 pi. That's 1 revolution over, what's the time it takes to do that? 24 hours. Do you all see that this right here, this over this, is the angle you go through, right? This is the angle I traveled through, divided by the time it took me to go through that angle. This is going to have a name in a minute. This is the total angle I traveled through, divided by the time, divide over how long it took me to rotate through that angle. So I went through a full revolution in 24 hours. All right, let's do this. Multiply this. Three, 4, 3, 0 times pi. Oh, times 2. Divide that by 24. And you get, who gets it? Who's got it? 897.9, 0.98, something like that. What? Miles per 24 hours. Did y'all? Oh, we did divide by 24. I apologize. We did. So this will be miles per hour. Yes.
Will we always multiply by 2 pi?
If it's a full revolution, yes. And the reason we knew it was a full revolution is because on Earth, we know it takes 24 hours to go around once, right? So 2 pi is always the substitute for 1 revolution. So right now, relative to the center of the Earth, right? Like if you could be standing at the center of the Earth, if you could, right here, not center of the Earth, on the axis, looking straight out to San Antonio, and you'd see us, we're going around that point, right? Like that. Our straight line distance right now, we're all moving at roughly 900 miles an hour right now, relative to the axis of rotation on the Earth. Question. If we were at the equator, would we still be going 897 miles per hour? I see a no. Would we be going faster or slower?
I would say faster because the radius is higher.
Yeah, so if you're here at the equator, it still takes 24 hours to go around a full revolution, right? But your circle's bigger, so you have to travel further distance, don't you? So you go a bigger distance over a smaller time. So the speed of a point on the outer edge of the equator of the Earth is traveling at a faster rate than us in San Antonio. It's kind of weird, right? What if you're at the North Pole? What's your linear speed? 0. You're going like this, right? You're actually not moving anywhere. You're just spinning. That's all you're doing, right? But as you go a little further out, right, as you start to come down like this, then you're actually going a distance. It's still 24 hours, but the further down you go, the bigger the circle you have to swing through, right? Why doesn't it feel like we're traveling almost 900 miles an hour right now? Gravity, yeah. I mean, we are stuck to the Earth, yes. But why doesn't it? I mean, like when I step outside, it's not like winds come, take me. And this is actually kind of an interesting question. Like, why does it not feel like we're traveling fast right now? Okay, so your body, when you feel like you're traveling fast, the only thing the body can sense is acceleration. That's the only thing we can sense. So if you're sitting in your car at a stop sign, you close your eyes, you're just there, right? Okay? Now, you step on the gas, you'll feel it, right? You'll feel it. And then you get up to a certain speed, you hit the cruise control and hit set, close your eyes again. I recommend you do this as a passenger, not as the driver, right? If you're doing 60 miles an hour down the road with your eyes closed, other than the sound of the air, you wouldn't know you're going 60 miles per hour, right? It's the only thing you can ever feel is deceleration or acceleration, any change in your speed. But if you're sitting at a constant speed, you don't feel it. So that's why we don't feel like we're moving, because we're already in motion, right? It's kind of interesting, yes? So you've got the Earth, and we're spinning, right? Spinning around there. But the Earth itself, right, is going around the sun. So not only do we have a speed around here, but we also are moving through around the sun, right? And then the sun is moving within our galaxy. So we're actually traveling a lot faster than this right now relative to the universe. So we don't know, though. It doesn't matter to us because we're not speeding up or slowing down. Now, if the Earth just decided to stop rotating, I said, you know, I'm going to stop rotating, we would feel that because we would have to decelerate. We'd feel that happening. And then again, the air outside, right, it's moving as well. Like it's moving with us. All the air is rotating around the Earth, so it's in motion too, so we don't feel it. All right, let's move on. I think I'm ready to just talk about one last thing here, and then we'll move on to the next section. So what we've used a few times now is this, well, we've been using this formula right here, right? And then every time we've done this, we've broken down the top to be r times theta over t, right? And this theta over t was always something, like in the last two problems, the theta over t is something that we were given, right? The bicycle tire, it was 50 revolutions per minute, right? It went round. It went 50 times 2 pi over 2 minutes. Or was it a minute? 1 minute? Something like that, right? That we were given. In the Earth spinning, it was 2 pi over 24 hours, right? This piece right here is used so frequently that we give it a name. It's called omega, and what it is, it's called the angular velocity. The angular velocity. And all it is the angle you turn through divided by the time. So omega is theta over t. It's just another name for this expression right here.
So is that a U next to the L? Or
This is a U. Angu, yeah, I started to write an L. Yeah, sorry. There we go. Angular velocity. So if I wanted to, I don't have to, but if I wanted to, I could rewrite this formula as r times omega, right? Because if this is omega and that's r, then r times omega is going to be equal to our linear speed. So there's like a couple of different ways we can look at linear speed. Linear speed is the arc length over the time, or it's the radius times the angle over the time, or it's the radius times omega, where omega is your angular velocity. All right, let's move on. We're going to move into the next section, 7.2. So please make sure you finish up that homework assignment if you haven't done so. For 7.1, I said don't worry about the last few problems, right? You should be able to get back in there. It should allow you to get access back into the assignment and you can finish up those problems. 7.2. All right, this section is called right triangle trigonometry. Now, trigonometry is a long word, so from here on out, I'm just going to write trig. Right? Trig. So right triangle trig. So I'm going to start this out by drawing you a couple of pictures. So let's say I draw you a triangle, and it's going to be a right triangle. What I mean by right triangle is one of the angles is 90 degrees. Now, we talked a couple of classes ago about when you look at a triangle, all the angles within a triangle have to add up to be 180, right? As long as we're talking about Euclidean geometry on a flat sheet of paper. So we know this is 90, which means these two have to add up to be 90, right? And that way the total is 180. That is a right triangle. We're all comfortable with that? So if you were to take, let's say you were to label these sides. Let's label this side A, let's label this side B, and let's label this side C. We all are coming into this class knowing the Pythagorean identity, right? I think I've mentioned it before. We all know, and I'm not proving this, that a squared plus b squared is c squared. Right? We're accepting this. We're accepting this. For a right triangle, this is true. Okay. So we know that about this. But what you may not know is this, that if I draw another triangle that has this same angle, right? This is an angle right here. Let's call it theta. If I draw another triangle that has this same angle but maybe goes a little bit further this way and goes up, let's see, extend this over like this and straight down. So this is another right triangle. See that one? That's a bigger triangle than the original blue one, right? And this distance from here to here, let's call that A tilde. That's just a symbol, okay? The tilde symbol. It's just so you can distinguish it from this little a. This is a different little a, but I put a tilde so that they're two different a's, okay? So a and a tilde obviously are not the same, right? This is a tilde. Now let's call this side from here to here, let's call that b tilde. Tilde, T-I-L-D, tilde, T-I-L-D-E, I believe. Tilde. There's a key, I believe that's right. There's a key on your keyboard. Your keyboard has that key somewhere. Yeah. I think it's tilde. Pretty sure. All right, so we're okay with this identity, right? Like right triangle, a squared plus b squared is c squared. But how about this? Did you know that if you take the ratio of any of these sides, it will be equivalent to the ratio of any of these sides? Oh, I forgot to put something here. I forgot to put from here all the way to here. Let's call that c tilde. Okay, so it turns out that the ratios are always equal. So that means I could write this down. B over c is equal to b tilde over c tilde. So if you take this side of this right triangle and divide it by this side, it's the same as taking this side of this right triangle and dividing it by this side. You follow? Take this side of the blue triangle and divide it by the hypotenuse from here to here. Whatever that ratio is. Like let's say this is the number 4 and this is the number 5. Right? I'll just put it here. Let's say that this is 4 and this is 5. Then this is saying that if you take 4 and divide it by 5, that will be equivalent to whatever this side is divided by this side. Those two ratios must be the same. And that works for all the different combinations you could think of. So if I do a divided by c, that's equal to what? A tilde divided by C tilde. Now, you have to believe this. I'm not proving this. We could prove it with some other stuff, but we're just going to have to take this on faith. Okay? This divided by this would be equal to this divided by this. This divided by this would be equal to this divided by this. What other ratios could I come up with, do you think? It's any ratios that you can come up with on this triangle. So what else? B over A? I could do B over A, right? So B over A should be equal to what? B tilde over C tilde. This is because these triangles are what we call A tilde. B over A should be equal to B tilde over A tilde. These are similar triangles. All similar triangles have a property that congruent sides are proportional to one another. All right, so, or I should say, hold on. Similar triangles have the property that corresponding sides are proportional. So whatever two sides are corresponding, this and this, it'll be proportional to this and this. Or we can go this and this, and it's proportional to this and this. You can do that for anything, all right? Got it? So if I draw a bigger triangle, right? Let's say I draw a bigger one that goes out even further, and goes up even further, and down further like that, like this, right triangle. And I call this one, this side over here, I can't call it B or B tilde. Maybe I'll call it B prime, okay? And then down here, I call this A prime. And then from here all the way up here is, you get the idea? C prime. We have the same things. You could replace all these tildes with the primes, or you could replace all the A, C, B, A with the primes. All of these relationships are always the same. So really, when you're looking at ratios of sides, the only thing that dictates the ratio is the angle. If I change the angle, doesn't it change all the relationships in the triangles? I'll say it again. The only thing that controls these ratios, the only thing that makes a difference, changes these values, is if I change the angle. Therefore, these ratios are kind of controlled by the angle, right? Change the angle, change the ratio, right? If I manipulate this, I have a different output over here, don't I? Change the input, changes the output. That's what functions do, right? Think about just functions from college algebra. If I define a function like this, right? You plug in something, right? And it has an output. If I have a different input, I have a different output, right? Input, output. So what we want to start doing is thinking about this theta as being the input of a function. And what comes out as the output are these ratios. So let me try and, let me kind of formulate that a little better. This was just to give us like a geometric kind of view of where we're headed. I want to keep a triangle up here. I'll have to draw a new one. So I'm about to define a function for you. We now define a new function that we can add to our, we've learned a lot of functions, right? In college algebra, you learned about polynomials, rational functions, exponential functions, logarithmic functions, right? Now we're going to define a new function, right? Sorry, my eyes, they bleed into my ends and it looks like W's. That's what that's supposed to be. We now define a new function. It is called the sine function. And here's how we define it. We're going to draw a right triangle. We're going to call this side A, this side B, this side C, and this theta. That's the picture I just drew a second ago, right? I'm about to write it down, but before I write it down, I just want to kind of remind you, remember in college algebra when we were doing the exponential function and you did like e to the, I don't know, x squared, something like that? This is what you put, you're putting this into the e function? Or you did like log, natural log, and then you had something in here? This right here is just the name of the function. This is called the natural log function. And this is what's being put into it. This is called the argument. The argument of the function. All right? So the argument is what's getting plugged in. I'm defining this new function, sine of theta. And the way I'm going to write it is this. I'm going to write sin parentheses. That's letting you know I'm talking about a particular function called sine. And then the input over here, we normally use x in college algebra, right? But because this is a function that involves triangles and angles, my input variable is going to be theta. Now it could be x. It could be. It could. But just because we're talking about angles, I'm going to say theta. So sine of theta, by the definition, is simply this number divided by this number. It's that ratio, b divided by x. I said b divided by x. B divided by c. Sorry. B divided by c. That's it. That is the definition of the sine function. All right? Let's not make it any more complicated than it has to be. That is the definition of sine up to this point in this class. That's the definition. So let's do an example. Let's say, as an example, I give you this triangle, okay? I tell you this is theta. I tell you this is, let's say, 4, and I tell you that's 5. And I ask you now to find sine of theta. What's your answer? 4 over 5. 4 divided by 5. That's your answer. Okay? That's it. We're done. You want to do another one? Find sine of theta. What's different about this problem? Did I give you what you needed? I did not give you what you needed. According to the definition of sine, you have a right triangle. Here's the angle. You need to be looking at this side over here, which is the one across from it, right? Across from the angle. We actually call that the opposite side. And then we need to take that and divide it by this number, which is actually the hypotenuse of this, right? So over here, I've not given you the opposite side, have I? I've not given you this. We need that, don't we? We need this. This is like the b, isn't it? We need to know what it is. And once we know what b is, we divide it by the c. So anyone have an idea of how we could figure out what b is? Yeah, we do have two other sides, don't we? This is a right triangle. We know what this is, and we know what this is, right? So in order to do this, this is going to be b over 5. Agreed? It's b over 5. I just don't know what b is. So to get b, I use the Pythagorean identity that says you take this squared plus this squared, it's this squared. So 3 squared plus b squared is 5 squared, which means 9 plus b squared is 25. Subtract 9 on both sides. You get b squared is what? 16. And final step, take the square root on both sides. So b is what? Plus or minus 4, right? Because you took the square root. Anytime you take square root, you have to do plus or minus. However, I'm only going to look at the plus y. Yeah, I'm not going to have a negative distance. Later on we will, so we have to pay attention to this. Right now we're talking about a triangle, and the length of a side of a triangle is always positive. So that's why we're going to get 4 here. So what's my answer? 4 over 5. Right? Yes?
You're saying right now, we only need to worry about the positive. That's it.
Only what?
You said we only need to worry about the positive end right now.
That's right, because this is a length of a side of a triangle which wouldn't be negative. But later on, we're actually going to have negative. It's going to be weird. Just wait till we get there. For now, just remember the sides are always going to be positive. All right? So this sine definition, that's the actual definition of it. It's just if you just need to know what this side and this side are. As soon as you have them, you just create the ratio and you're done. Now, if we call this side the opposite side of the angle, and we call this side the hypotenuse, well, we call it the hypotenuse, okay? The hypotenuse is the longest side of a right triangle. Then sine, another way you could think about sine is it's the opposite, right, divided by the hypotenuse. Is it all right if I write it that way? So one way to look at the sine function is to say, hey, sine is the b over c, or it's just the opposite side divided by the hypotenuse. Do you all understand that you would get the same answer if you drew if I draw a bigger triangle, right, like this, and I do opposite over hypotenuse, that we're going to get the same answer for sine because they're similar triangles? Right, so the only thing dictating this is the angle. Change the angle, then you're going to get a different value. All right, that's the definition of sine. The next function we need to define is cosine. So now we define cosine. The cosine function is the same picture. A, B, C, here's theta. By definition, the way we write it is we write cos, parenthesis theta, and this is going to be A over C. So you're taking the side right next to the angle down here, and you're dividing it by the hypotenuse. The side that's right down next to theta, we call that the adjacent side. And of course, this is the hypotenuse, right? So another way you could look at this is that cosine of the angle is adjacent over hypotenuse. Any questions? There's 4 more trig functions. There's 4 more. The next one is called the tangent function. And it's the same picture. A, B, C, theta. And tangent of theta is written tan with the theta, and it's equal to b over a.